Hello ladies and gentlemen, welcome back to your next video lesson. What we're going to be talking about today is expanding on what we've been talking about with with polynomials and the rational root theorem. The two particular skills we're going to be looking at today is how do you create a polynomial written in standard form when you're provided the roots, and in this case the roots are not necessarily all going to be positive, or real I should say, that we're going to have some complex roots at this point. And how can you factor polynomials using the rational root process, even though all of the roots may not be rational at all. This is where we're going to start seeing some complex roots being mixed in with the polynomial stuff that we've been talking about. Now here, what this is telling you, the fundamental theorem of algebra says that every complex polynomial has, of whatever the degree is, has at least one complex root, which is a little misleading in my opinion. If you have a complex polynomial, you're not going to have one complex root. Complex roots always come in pairs. So here where they're saying you'll have at least one complex zero, that's true, but really you should have at least two if it is a complex polynomial. Now it won't look complex, the polynomial itself. It'll basically just kind of look, like a normal polynomial will be to whatever the degree is, but some of the roots will be complex. And here it's kind of letting you know basically what we've been talking about is that whatever the degree of the polynomial is, there should be that many roots, whether they're real or complex. So moving on, keep in mind that here we're going to be talking about how the first skill that we're going to be practicing is how you write polynomial in complex form, or rather, let me backtrack that a little bit, how you write a polynomial in standard form if the roots are non-real, if the roots are complex. Now keep in mind the A component is a real part, the BI component, that's the imaginary part. Together it's a complex number. So here, keep in mind, this is also something that we've talked about. It's been a little while since we had to look at complex numbers, but whenever we were solving complex numbers before, they always came in pairs. And those pairs are called conjugate pairs, meaning if I have 3 plus 2i, its conjugate pair is going to be 3 minus 2i. If I have negative 2 minus 3i, its conjugate pair is going to be negative 2 plus 3i. It's been a little while since we've talked about it, but don't forget that it is a particular skill that we're looking at, and it's kind of talking about what I was at the very beginning of the presentation when it said if it's a complex polynomial, there's at least one. Well, really, there's always going to be at least two, because complex roots are always going to come in pairs. The reason why, again, they always come in pairs, the complex roots generally are going to come from some quadratic expression of some kind. And since a quadratic expression is a second degree polynomial, that tells you that if there is one complex root, there has to be another one. So for instance, if I have x squared plus 4, if I set that equal to 0, I'm going to get x squared equals negative 4. If I take the square root of both sides, that's going to give me the square root of negative 4, which tells us, well, there's our complex roots. That'll give me a positive or a negative 2i. Because we have to take the square root of something at some point when we're solving a quadratic expression, then that's why we always have two complex roots. If I have one, I have to have two. So here what we're going to do is just a quick multiplication. It's just a quick reminder. This is something that you've seen before. If you multiply conjugate pairs together, you should wind up with one real number left over. Now here, the a term may very well be like x plus something, is if the a term itself isn't a real number. So, but again, if we're multiplying conjugate pairs together, we should wind up with a real number. But just to show you again through the FOIL process why, a times a is a squared, a times negative b will be negative ABI. BI times A will be a positive ABI, and BI times negative BI will be negative B squared I squared. Please keep in mind, when you're multiplying the complex parts together, you have to multiply the a's too. So here you see the complex parts in the middle cancel each other out. And if you recall, I squared is equivalent to negative 1. So a squared plus or minus b squared I squared is the same thing as saying plus b squared. And both of those generally are going to represent some, number, whether it's, 3 or 1 or 2 or something, and you add them together and they give you just one real number. Okay, and we're going to go ahead and just, you can write that down if you want to, but let's go ahead and get into the descriptions here of things. Now, the first thing that they're going to be checking for, not necessarily telling you to do this, it's just one of the things that as a student you have to be recognizing, that imaginary numbers always come in pairs. So here, we're not asked to write this out as a 5th degree or 6th degree polynomial. It's just asking us, what are the remaining zeros? Well, here, they're giving us 1, 2, 3 zeros out of the 5. So there's 2 that we need. But because we have 2 imaginary roots, then we have to recognize that those imaginary roots always come in pairs. So the conjugate pair of the 3 plus, or the 3 minus 2i is going to be 3 plus 2i. So there's one remaining root. And the other remaining root is going to be the conjugate pair of I, so that would be negative I. Here in the 6th degree polynomial expression, we have 1, 2, 3, 4 real roots, and then 1 complex root. So the remaining root for the 6 that we would need would be the conjugate pair of the negative 2 plus 5i, which would be negative 2 minus 5i. Now, if we can understand that, then we should be able to multiply them together. But before we do that, let's see how it's going to work, because there is an expression, a little shortcut that we'll get that we can use when we're multiplying conjugate pairs together as a factor. But I will say, I'm going to show it to you guys both ways. I'm going to show it to you as, straight multiplication, and I'm going to show it to you as using the little shortcut that we're going to get here. Because in my experience, students will remember this particular shortcut for the short term. It's not something that you do a lot of. It's not something you do enough of to generally commit it to memory. So if you can remember it at least for a little while, it'll help you out on your homework assignments and maybe through your test. But if it comes up again on, say, like a semester exam or a final exam or something for your CLEP tests, months from now, you may not remember that. So you need to have the algebra skills to remember your order of operations to multiply these things together. But let's go ahead and show you what it'll be. And if you can remember it for the time being, use it. If not, just use your normal order of operations. So here we have 2 factors that represent just conjugate pair factors, okay, in no particular numbers. But we're going to multiply these things together, normal kind of FOIL process. So x times x will give me an x squared, and the x times the negative in front of the complex number will give me negative x times whatever that complex number is, a minus bi. Okay, well, now we're going to multiply the next parts together, and I'm going to put a bracket around here so that way we don't get the parentheses confused. So now we're going to take this complex number, multiply it to the x and to its other conjugate pair. So negative times the positive for the x will give me negative x times whatever that complex number is, a plus bi. And here, when we multiply, the negative signs in front of each of the complex numbers would give me a positive. And so we're going to just write them out, showing that we're multiplying them together. A plus bi times its conjugate, a minus bi. Okay? Now, inside of the hold on, let me backtrack here for just a second. I don't really know why I put these parentheses here. They're not necessary since we're foiling it out. We're not multiplying more than one thing together, so my apologies for that. So let's go ahead and see what we get if we distribute everything, multiply everything that we have left over. So the x squared, there's nothing to do with him right now. The negative x here can be distributed into this parenthesis, which will give me negative ax and positive bxi. Here again, I can distribute the negative x and get negative ax and minus bxi. And then the conjugate pairs together we have to FOIL. So here, again, you can apply the little shortcut that we have here as far as saying a squared plus b squared. But let me go ahead and just demonstrate what happens. So a times a is a positive a squared. A times a negative bi will be minus abi. The bi times the a will be plus abi. And the bi times the negative bi will be negative b squared I squared. Again, most common mistake is that students are going to forget to square the I when you multiply those last two things together. Okay, so let's keep going. Combine our like terms. So negative ax and the negative ax will give me minus 2ax. The positive bxi and the negative bxi cancels. So now I have the a squared and negative abi and positive abi cancel, and b squared times I squared, negative b squared times I squared rather, will give me plus b squared. So here is the shortcut expression when we're multiplying conjugate pair factors together. And it's a very helpful rule, very useful when doing this, but again, we just generally don't do it enough for it to really be committed to long-term memory. So if you don't remember that rule or how to get it or what the rule is, you just have to kind of go fall back to your normal order of operations and multiplying and combining your like terms. So let's go ahead and see what we have here. This is the first example that we're being asked to write a polynomial in standard form when they're giving us two of the 4 zeros that we need. So we know it's a fourth degree, so we have to have 4 zeros, but they're not giving us all of the zeros. But that's okay. If they're giving us two complex zeros, then we should recognize that they always come in conjugate pairs. So even though they're only writing down what two of them are, they're really giving us all 4 of them. So what we're going to do is write this fourth degree polynomial in standard form, and we're going to start with the first 2 zeros, the 2 i's. So if I take the one that was given to me and I write it in factored form, I'm going to say x plus 2i, and so its conjugate would be x minus 2i. Now these are going to be much easier to multiply because the real component, the a part, is just 0. So those are much easier to multiply than what we're going to have for the second part. So the conjugates that or the factors that we're going to get for the other 2 roots are going to be x minus, and we're going to, and here, this is where I want to put the brackets. This is where we're going to put these in parentheses. We're going to say x minus both of these factors, 1 plus I. I don't know why I'm having a breakdown in my train of thought here. And we're going to say x minus its conjugate pair, 1 plus, oops, sorry, its conjugate pair is the minus I. Minus I, pardon me. And now we're going to just multiply both pairs together. So I'm going to multiply each pair kind of at the same time, so that way we don't have to, really make this a long problem. So here, x times x, x squared, and again, I'm going to keep this in parentheses for the time being because I'm not distributing it to the other side yet, minus 2xi plus 2xi when we multiply those terms together, and then negative 2 times positive 2 will be negative 4i squared. Okay, so now we're going to FOIL these two together, and I'm going to show it to you both ways. I'm going to do it the long way with normal order of operation stuff, and I'll show you the shortcut so that way you can see both ways. X times x, x squared, x times the negative conjugate that we have will give me negative x times, oops, I want to write another x for some reason, times the 1 minus I. And then the negative in front of the 1 plus I times x will be minus x times its complex number, 1 plus I. And then the negative signs in front of both of the complex numbers multiplied together will be positive, and we'll just say one complex number times the other complex number. Okay, so again, it's, if you can remember the shortcut, it's going to be real helpful for you, but if you don't, you need to make sure you go through the process. Again, just be calm, be patient, try not to lose track of your signs, and you should be okay. So here in the parenthesis on the left, we're going to just combine our like terms. So I'm going to have x squared. The negative 2xi and the positive 2xi are opposites. They cancel out, which they should. And we have plus 4 because I squared is negative 1. Negative 1 times 4 is positive 4. And so now let's see what we get here. So the x squared is just kind of x squared by itself. Distribute the negative x into the first complex number, and we'll get negative x plus xi, and distribute the second x into the second complex number, and we'll get negative x minus xi, and then FOIL here. And again, if you remember the little shortcut for multiplying conjugate pairs together, then you can use that. Otherwise, just write it all out. So the 1 times the 1 is 1. 1 times negative I is negative I. Positive I times 1 is positive I. Negative I times positive I is negative I squared. So x squared plus 4 isn't really doing anything yet because we still have to simplify the stuff in the parentheses on the right. So we have x squared, and negative x and another negative x will give me minus 2x's. The positive xi and the negative xi cancel. The positive 1 and the I squared is also going to be a positive 1. So the i's cancel there, so we're going to have plus 2. And at this point, we can multiply both of these expressions together. X squared times x squared is x to the 4th. X squared and the negative 2x will be minus 2x cubed, and so on, plus 2x squared. And then multiply the 4 through, and I'll get a positive 4x squared here, minus 8x plus 8. Add those two together, I'm kind of running out of room here, so we'll just say f of x here is equal to x to the 4th minus 2x cubed plus 6x squared minus 8x plus 8. So that's the final result that we should get, and that's how we get it if we don't remember the shortcut. Now, particularly, I want to look at how the shortcut method would be employed multiplying these two terms together. So at this point, and I'm going to just kind of do this off to the side here, we have x minus 1 plus I times x minus 1 minus I. Okay, so if we multiply these together, we do it the long way that we had there. But the shortcut that we had was x squared minus 2ax plus a squared plus b squared. Not exactly the easiest thing to remember, but again, for the short term, if it helps you out, great. You might want to take a habit of just writing it down on your homework every time you use it, so that way you can remember it for a quiz or a test, and hopefully long term, if you see it again on a semester exam or a CLEP test, you'll be okay. So keep in mind, this is the a value. The b value that's in front of the I here is also a 1. So those are the numbers that we substitute into the shortcut expression here. So we say x squared minus 2 times 1 times x plus a squared, which is 1 squared, plus b squared, which would also be 1 squared. So we get x squared minus 2x plus 2, and much less work, much shorter time than it took us to get it here. But either way you want to do it, I'm going to show both ways for anybody that needs to do them. So next example, again, fourth degree polynomial. They're giving us 2 real roots and 1 complex root. So it's the second complex root is going to be the 5 minus I as a conjugate pair. And let's go ahead and set this guy up and multiply him through. So we have I'm going to do the 2 real roots first. So we're going to get an x plus 1. X minus 1 is the 2 real factors. And then the complex factors, I'm going to have x minus, and I'm going to write the one that they gave us first, 5 plus I, and its conjugate pair to be x minus 5 minus I. And multiply both sets of factors together at the same time. So x squared, or x plus 1 times x minus 1 will give me x squared minus x plus x minus 1. Here, x times the negative sign in front of the complex root will give me, well, x squared first, and then minus x times 5 minus I. And then same thing, the negative in front of the complex root of 5 plus I times x will be minus x times 5 plus I. And then the negative signs in front of both of the complex roots, negative times negative, will be positive, and then we just write the 2 complex roots down, 5 plus I and 5 minus I. Combine your like terms in the parentheses on the left, and we get x squared minus 1. Now, before we combine our like terms on the parentheses on the right, we have some more work to do. So the x squared is just the x squared. Distribute the negative x here, and that'll give me minus 5x plus xi. Distribute the negative x here, and I'll get minus 5x minus xi. And then FOIL these 2 terms together, and I will get plus 25 minus 5i plus 5i minus I squared. So x squared minus 1 isn't doing anything yet. Combine all of your like terms in the parentheses on the right. There's no other x squared term. Negative 5x and negative 5x gives me negative 10x. The xi's cancel, and the negative 5i and the positive 5i cancel, and I squared is the same thing as positive 1, so 1 plus 25 is 26. Now I can multiply the 2 expressions together and see what we get. So x to the 4th minus 10x cubed plus 26x, and then multiply through with the negative 1, and that'll give me, oops, squared, negative x squared plus 10x minus 26. And so we're going to get f of x finally to be x to the 4th minus 10x cubed plus 25x squared plus 10x minus 26. And again, let me just show the shortcut method for multiplying the 2 complex factors together. So here we have x minus 5 minus I and x minus 5 plus I. Again, x squared minus 2ax plus a squared plus b squared. Again, doesn't really roll off the tongue very nicely. It's not the easiest thing to remember, but if you can remember it, it'll help. So x squared minus 2, the a term in this case is a 5. The b term in this case is still just a 1. And so let's see what we get. X squared minus 10x. 5 squared is 25, 1 squared is 1, 25 plus 1 is 26. So either way that you want to approach it is fine with me as long as you get the right answer at some point. So now let's take a look at this next one. Here what we're doing is we're moving on to can we write the factored form from the standard form, and they're not giving us any factors to start with. So we're going to have to use the method that we did with the rational root theorem, even though that we don't know if all of them are going to be rational roots. So the first thing I want to do here for a problem like this is, based on what we've been practicing in class, check to see if 1 is a root. Now here, again, if 1 is a root, then if I take the coefficients and add them together, it should equal 0. And we can see, since everything is positive, that that's not going to work. So x, unfortunately, being equal to 1 won't work. So let's look for a negative 1. Okay, so for x, if negative 1 is a root, we have to change the sign of the odd numbered powers and see what we get. So the 1 for the x cubed would be negative 1 plus the 13 minus 57 and then plus 85. And if I add all those together, that's going to give me a 40. So 40 is not 0, so x, in this case, will not equal negative 1. So positive 1 and negative 1 don't work. So that's a little bit of work that we have taken away from us. The next thing I might want to check to see is how many positive roots or how many negative roots do I have. So positive numbers, if I, using Descartes' rule, if I substitute a positive number into the polynomial, well, that's going to give me 4 positive numbers, because if I substitute positive into everything that's already positive, none of the signs change. So there's 0 positive roots. So that means that there should be 3 negative roots, or 1 negative root and 2 complex roots. But let's just double check it with Descartes' rule just to make sure. So if I substitute a negative number into an odd numbered power, I get a negative. Then it'll be another positive, a negative, and a positive. So we have 1, 2, 3 sign changes. So yes, that's telling us that we should have 3 negative roots, or 1 negative root with 2 complex roots. So let's see what we get. Now we're going to start writing out our factors. The factors of 85 are 1 and 85 and 5 and 17. Those are the only factors of 85, and the factors of the Q term are just 1. So the possible roots that we could have would be a positive or negative 1, positive or negative 5, positive or negative 17, and a positive or negative 85. Now, using the rule of positive 1 or negative 1, we can scratch these out. We know that they're not going to work. And using Descartes' rule, we know that none of the positive numbers are going to work. So we really only have 3 negative numbers with which to try. So the smallest negative number now we're going to work with, negative 5. None of the exponents are missing, so we don't need any 0 placeholders. So 1, 13, 57, 85. Let's show that this is going to be a 0. Go through your synthetic division. And then we're going to get 8 here, and then negative 40 here, which will be 17, which will give me a negative 85 here. So we got a good root. So here we have, as a simplified polynomial, excuse me, x squared plus 8x plus 17. And can we factor this? Well, let's look at the discriminant and see what the discriminant gives us. The discriminant is b squared minus the 4ac of the quadratic formula. So if we say 8 squared minus 4 times 1 times the 17, that is going to equal a negative 4. Since the discriminant is negative, that tells you that we're going to wind up with two complex numbers. So we got 1, so we know x is equal to a negative 5, which the factor would be x plus 5. And so we know Descartes' rule said we could get at least one of those, maybe 3, but we got for sure 1. And looking at the discriminant of the simplified polynomial, the fact that the discriminant is a negative number tells me that the other two solutions have to be complex. So if you don't remember the quadratic formula, it's negative b plus minus the square root of b squared minus 4ac over 2a. So we're going to just evaluate the number that we have here, or the quadratic that we're left over with. So negative b would be negative 8 plus minus, we've already figured out the discriminant is negative 4, and 2 times 1 is just 2. So negative 8 plus minus 2i over 2 will simplify to be negative 4 plus minus I. So the remaining factors that we have are x to be negative 4 plus I, and x is negative 4 minus I. Oops, I don't know why I'm writing a parenthesis here. So we know the three roots, negative 5 and the negative 4 plus I and the negative 4 minus I. So the way that we would write it in factored form, we would take the factor, the one real factor that we have, x plus 5, and then we take the factors of the two complex answers that we have, and we'd say x minus, and if you want to, you can put a bracket there, negative 4 plus I, and x minus negative 4 minus I. And there is the third degree polynomial written in factored form. And the three solutions would be negative 5 and the two complex numbers that we have. All right, so here, moving on, this one, looking at Descartes' rule, or looking at the rule of positive 1 and negative 1. So positive 1, everything is positive, so that won't work, because there's no way that all positive numbers are going to make 0. So looking at negative 1, well, there's no odd numbers, there's no odd degree or odd exponents, so that won't work because none of the signs will change, so everything will still be positive. Okay, so let's look at Descartes' rule. If I substitute a positive number in, well, that will give me a positive, and another positive. So that tells me that since there's no sign changes here, that tells me that there are no positive roots. Okay, and if I substitute a negative number using Descartes' rule, a negative number to an even power is positive. So that'll be positive and positive. So that tells me that there's no negative roots either. No negative. So if there's no positive roots and there's no negative roots, then that means that all of the roots, all 4 of them, have to be complex. Okay, well, let's see, how do we want to approach this? Because if I don't have any positive roots and any negative roots, then finding out the factors of the p and the q's don't really help me. Well, this problem is written in such a way that we can actually treat it almost like if it's a quadratic. I know it's not a quadratic, but we can treat it kind of like it is. Meaning, well, let's look at the discriminant of what this would be. Meaning if this is A, this is B, and this is C, well, what would that give me? If I say negative, or if I say B squared minus 4AC, well, that'll be 13 squared minus 4 times 1 times 36. And if I do that, that gives me a 25. That tells me that even though it's a 4th degree polynomial, we can factor it kind of like we would with a normal quadratic. So let's go ahead and do that. We'll break this up to be x squared. So the factors of 36 that can combine to give me a 13 are going to be a 9 and a 4. So I'm going to say plus 9 and x squared plus 4. So if I set each of these factors equal to 0, then here I'm going to get x squared equals negative 9. So x is equal to the square root of negative 9. So x is equal to the positive or negative 3i. And here, x squared equals negative 4. Take the square root of both sides. And I get x to be a positive or a negative 2i. So those are going to be the 4 solutions that we have. So the way I'd write it in factored form, I would have x plus 3i times x minus 3i, and x plus 2i times x minus 2i. And that's pretty much where we're going to stop. There is one more example here on this presentation that I will probably demonstrate in class, but for time purposes, this video is already kind of going long. We're going to go ahead and stop it here. So if you have any questions, please make sure you have them written down, bring them to me in class, and see you guys soon. Thanks for watching.